In this video, I'm going to go over 3 problems that all shared the same property, that they involved ingesting an ASCII blob of numbers. So they're all slightly differently formatted, but they all have enough similarities that I wanted to try to make one parser that would be able to solve all 3 problems. So I'm starting off with the parser, and then I'm going through and doing the solution to all 3 of the problems. So my first step here is to look at the actual data I'm going to be parsing. And I don't have a spec for the data. I just have samples, and all I need to do here is invent a concept of how to think about the data that will work for these 3 samples. I'm not trying to make some kind of, parser to meet a particular standard or for a very well-known data generator. Instead, what I have is just these 3 samples, and I need to just come up with a simple rule that will work for these 3 samples. If it happens to later work for more stuff, that'll be great, but I'm shooting for making it work for just these 3 particular examples, and if that's as much as it ever does, that'll still be pretty helpful. So next, after looking at the samples, I sort of write down all the features that I saw, the things that are different between them and things that are the same between them. And then I kind of try to move the ideas around and look for a way that I could make the things that are actually different about the data not be a huge obstacle, right? So for instance, some of them are one-dimensional, just lists of numbers. Some of them are two-dimensional grids of numbers, and some of them are one-dimensional lists of very long numbers that are like one-dimensional lists within one-dimensional lists. So they're kind of two-dimensional in one sense and one-dimensional in one sense. And, I don't want to get bogged down in having lots of that look different in the actual parser. So I want to figure out a way that I can parse it just the same way no matter what the input is supposed to be, and reconstruct it in different ways, like in maybe secondary passes or something. I also want to deal with the fact that sometimes it's grouped in 2 digits at a time. So in one of the problems, I have 2-digit numbers in a grid, and in other problems, I'm looking at it 1 digit at a time. And sometimes I see spaces showing up in the middle of the grid. So in that one with the 2 digits per cell, there's also a space separating out each cell, but I don't have spaces separating out the others. So sort of the ideas I end up with here are we're going to ignore characters that aren't digits. We're going to be able to either group things by 1 digit or 2 digits at a time. And we're going to always parse it as 2-dimensional in the sense that every new line represents moving down to another row, and then we have arrays for each row. And the reason for doing it that way is that if I want to treat it as one-dimensional, it's fairly easy to do a sort of internal, reconsider the data as one-dimensional, because it's all going to be coming out in a flat array as well. But as soon as I want it to be 2-dimensional, I just need to know the pointers into where each line begins. So I'm going to have essentially a one-dimensional sequence of all the numbers, and I'm going to have the indexing to treat it as 2-dimensional as well. And that way I kind of can get it to work whichever combination of ways I need it to work by doing either a little bit of extra parsing or processing afterwards, or by just using the specific way to index into the data that makes sense for the problem. So that's the strategy I came up with by sort of toying with it. And now let's just go through the programming part real quick. So this problem says the 4 adjacent digits in the 1,000 digit number that have the greatest product are 9 times 9 times 8 times 9 equals 5,832. I've highlighted right there where the 9989 is. Find the 13 adjacent digits in the 1000 digit number that have the greatest product. What is the value of this product? So I'm skipping right into the programming for this problem because it turns out that there just really wasn't a lot to it. With the parser already out of the way, the only other thing to do here was to scan along the entire sequence and do all the multiplies of 13 adjacent digits at a time. And the brute force way to do that would involve 13 multiplies, well, 12 multiplies of 13 separate numbers for each spot in the sequence where you can actually get 13 numbers side by side. So it's not quite the whole sequence because out the end there aren't runs of 13 that start like 1 from the end and 2 from the end and so on, right? But we can actually do even better than that by just saying, instead of doing all 12 multiplies every time, once we get the process going, why don't we divide out the first, like the last thing that is in the window and then multiplying the new thing in the window. So each time we are moving along, we're just dropping something old out of the window of the 13 side-by-side numbers we're multiplying and multiplying something else in new. And then if we see a 0, we can just skip ahead to the end of the 0 because we know that whatever the result is going to be, if any of them are greater than 0, then the 0 will never be anything other than 0, so we can ignore it and skip through it because they're all going to be zeros as long as there's a 0 in the window. Hopefully that concept makes sense. I'm not sure if I'm explaining it exactly right, but the algorithm is just not that complex. So we just dove right in and started programming without really doing any blackboarding on this one, and there's not that much to discuss about it. So let's get to the next problem. In the 20 by 20 grid below, 4 numbers along a diagonal line have been marked in red. The product of these 4 numbers is 26 times 63 times 78 times 14 equals 1,788,696. What is the greatest product of 4 adjacent numbers in the same direction, up, down, left, right, or diagonally, in the 20 by 20 grid? So this was just a small modification of the algorithm for the previous problem. And then I had to take that modified version of the algorithm and break it down into about 6 different cases, or maybe 4 cases that are sort of reused in slight ways depending on how you want to count it. So the tweak to the algorithm is that instead of just striding along a giant sequence of numbers, I now have a 2-dimensional grid. And so, if I'm going to iterate across a row, I want a different stride than if I'm iterating down a column or across a diagonal, right? Iterating a diagonal is basically the same thing as iterating a column with like one more or one less, depending on whether it's a positive slope or negative slope diagonal that you're iterating, right? So I added in a variable amount of stride to the algorithm and changed the window to 4 numbers instead of 13. And then the rest of the problem is just breaking it down into cases. There's one case for it handling each row. There's one case for handling each column. And then there's a case for diagonals that go from top left to the bottom right. And that gets used twice, once to iterate diagonals that start on the top row and another that iterates diagonals that start on the far left column. And then again, I have another diagonal which goes from the top right to the bottom left, and 2 separate subcases for that in order to iterate the top and the right-hand side of the grid. Work out the first 10 digits of the sum of the following 100 50-digit numbers. So what they're saying is each line here is a separate 50-digit number. So when we parse this, what we're going to have is like this here, like each line we see, if we were to look at it in strides or something, each row of digits is one of our 50-digit numbers. The first one is the significant digit, right? So like that 3 there is a significant digit for this number. You'll notice there are no zeros in that column. So they're technically actually 50-digit numbers. They're not just sequences of 50 digits. They are 50-digit numbers. Right? The zeros can only appear in the other 49 slots. Otherwise, it would be a 49-digit number. So what it wants us to do is to say, suppose we were to take the sum of all of these. Then that would give us some number. We don't know what number that would be. It'd be big, but it'd be just some number. And if we can find the highest 10 digits, the 10 digits that represent the, what's the word I'm looking for? The most significant 10 digits from that sum, then we're done. That's our answer. So the interesting part of this problem is that a 50-digit number is too big to fit in a 64-bit integer or even a 128-bit integer. So I'm going to have to figure out how to do the arithmetic on numbers that don't fit inside of one register on my architecture that I'm programming for, right? So I'm going to start off by just practicing long addition. Basically, the idea here is I'm exploring how to build up the concept of addition of very large numbers using building blocks of smaller numbers. And that's basically what the sort of on paper long addition algorithm is, right? Where you sum the first digit and then you have a carry sometimes, and then you sum the next digit and you add the carry in, and then you keep going until you're up to the highest digit all combined together. That's just a way of adding two big numbers using the knowledge of how to add smaller pieces of each of the number broken down as digits. And my thinking here is I can do the same thing using like 64-bit slots, and I end up going and calculating that it's going to take 3 64-bit slots in order to contain a 50-digit number and to contain the sum of several, well, I can't remember, what was it, 50-digit numbers or 150-digit numbers, however many are in this problem. And so since 3 64-bit integers will be able to form a number big enough to get the answer for the problem in those three 64-bit values, I'm basically thinking of it as a 3-digit number, where by digit I mean number that goes from 0 to 2 to the 64 minus 1, right? That's my new numbering system. So instead of going from 0 to 9 like a base 10 number, it's a much larger base, but it's still the same basic concepts. So first I'm practicing the addition stuff. I'm also going to then do the addition stuff again, but instead of plugging in example numbers, I'm plugging in sort of variables. And with that, I can sort of see how the variables connect in an abstract version of the addition algorithm. Next up, I double check that I understand how carry is going to work, and I confirm that when you add two numbers, you can never have a carry of more than one. And I also go and look into the low-level instructions on x64 that are going to be necessary here. So I look at the add instruction and see how it tells us about the carry bit, and luckily it does. It sets a flag inside the processor whenever the addition of two numbers would involve a carry. And then there are a few different ways we can find out about that flag. The one I end up going with here is that I look at a jump instruction that jumps conditionally if the carry flag is set. And so putting all that together, I can then plan out the actual detailed low-level algorithm that I'm going to write that involves when to add numbers, how to combine each piece of information using the building blocks of computation that I actually have available to me on the architecture. The next issue that comes up that I have to handle is that the numbers that I actually have, the input to my system here, isn't in a 64-bit by 3 number system. It's just in decimal numbers, right? I just get a sequence of numbers that are 10, like base 10 digits, and I need to convert that sequence of base 10 digits into my 64-bit by 3 numbering system that I've built up. And so I need to be able to do decimal conversion to the U64 by 3, and I need to be able to also do U64 by 3 back to decimal, because at the end of the problem I need to check the top 10 digits. That's the original problem to solve here. So if I just am stuck with a U64 by 3, that's also no good. So I have to be able to convert back and forth from decimal representation to this new representation that I've invented that I can do the addition for. And so that makes me think I'm going to also need to just do some form of long division and long multiplication. It doesn't have to be the full thing, but I need to be able to at least multiply and divide by 10, because that's how I can do conversions between another numbering system and base 10. So the same process that I used for coming up with the plan for the addition, I use it again for coming up with a plan for how I'm going to do multiplication and division with this new numbering system. That process again is just I write down an example of the kind of problem by hand, just using normal base 10 numbers to sort of see the pattern. So I do a multiply of a 3-digit decimal number by a single-digit decimal number, and then I do it again, but instead of plugging in a real number, I just use abstract variables so that I can see how the variables are going to connect to each other. I also verify that all of the extra values, in this case the overflows from the multiplies, are always going to fit inside of a single register, which they do. And then I look at what the instructions can do on x64 and come up with the plan of how the computational version is actually going to work detail by detail. So one thing I want to emphasize here is I didn't do full 3-digit number by 3-digit number multiplication or 3-digit number by 3-digit number division. I simplified it to 3-digit number by single-digit number because that actually makes both of these algorithms a little simpler. The other thing I wanted to point out is the division algorithm just ends up being super, super clean. And this is because the division instruction, it takes in 2 numbers as a numerator and 1 number as a denominator. And then it outputs 2 numbers as output. One of them is the quotient and one of them is the remainder. And it always outputs the quotient to RAX and the remainder to RDX. But what's interesting about that is RDX is also always the high bits of the 2 slot input for the numerator. So when I look at what I actually need to have happen in long division, the remainder from one stage becomes the high digit or the high slot of the next divide, and the architecture is already defined to put that value into the register where it will be needed. So it almost becomes like super obvious that this instruction was probably designed specifically to make something like this really clean and easy, because all we end up having to do is basically run the division instruction multiple times with an extra move in between to reset the low digit of the numerator each time. It's really cool. Anyways, so that's the planning phase. After this, we get into programming.